Hello, I'm back. Let's review the beam cross sections, and we already studied about the beam cross section, but it was a little bit confusing. So I would like to clarify the beam cross sections before deformation and after deformations. This one, this beam is the before deformation. So this one subject to a bending moment M. Bending moment M. And then okay, this one is the before deformation, okay? And the length we consider was dx. And after we apply the M here, this straight beam will deform, especially these cross sections. This vertical plane will move, rotate here. So the rotational angle will be, as you can see here, d theta. So if we draw here, that was the original vertical plane, and this is the amount of the angle rotations. And what we observed that dx d theta, actually this was the R, radius curvatures. This is the R, and that was the 1 over R. Actually, this equation was obtained, R d theta is a dx. Right, R times dx was the that is the okay. This is the length, but that one is the same as the before deformation. So that is the dx. So that is a basically deformation observation, very important. And if we plot them here. Again, it's the same figure, but I'd like to explain a little bit in different way. Say we have a beam with the length L and clamped here. Clamped means I'd like to observe the deformations of the right-hand side with respect to a left-hand side. So let's say we apply the moment M. And then this the cross section will rotate, and here the rotational angle will, I will say, the theta 0. Now remember we are considering length L, and this angle, the cross section, originally was the vertical. Right, vertical, and this one is now is theta 0. And actually, we have a many vertical line which will indicate how much the cross section rotate. So say this one rotates, say this much. So this one, the first one, will rotate this much and that much, and gradually increasing until theta 0. So that is actually what's happening. So as you can see that the theta is gradually increasing along this x. This is the x-axis. So d theta dx, we can say that the theta 0 at L. Okay, theta 0 at L, and that is the same as here. Dx d theta, theta 0 L. Of course, this one, if this one is the radius of R, which is the curvature, inverse of curvature, and that is the 1 over R. And after beam theory, what we observed was that d theta dx is moment m, which is the applied, we apply the moment. We can say the m0, which is applied to at the cross section at x equal L, and E I is the moment of inertia. So this dx d theta dx is the theta 0 and L. So theta 0, the rotation at the cross section at x equal L will be simply m L and E I z z. So this is the angle of rotation for the bending case, and I hope this explanation is more clear than before. Okay, but please notice there is analogy between bending and torsion and so on. And for the torsion, we had a phi and torque and L and G and IP. And for the bar, delta was the deformation, and the force P and L and E and A. And these are three equations for the deformation for each case: beam and shaft and delta. Okay. Next point I want to observe is that similar to a torsion case, similar to the torsion case, let's consider a beam with a series and parallel connections. You can say that we have two beams connected, but on the left-hand side is the clamp and the right-hand side is a free. And this is the length L1 and length L2, and this is a E and I will just call E1 and I1, and this is a E2, I2, and at the end, this beam is subject to the moment M. Now, we want to solve how much the rotate, this cross-section, how much it rotate, and how much these cross-sections rotate. So that's what we want to calculate. Okay, to solve this one, this is the beams in series connections. To solve this one, of course, we need to follow the steps. First is equilibrium. Equilibrium, we can say that there is a reaction force that was unknown, but using the equilibrium, we can see that this is a simply bending moment, which is the same as the moment we apply. And then we also apply the moment force equilibrium at each beam. So this is the M, and obviously there will be a M. And the second beam, we have a moment M, and there will be a moment. So this is obvious, and we can get this all the M reaction forces, reaction moment, using the moment equilibrium. Now we want to calculate the angle of rotations, and I will call theta 1 with respect to theta 1 of these cross sections, and with respect to the left hand side, and this theta 1 is simply moment and L1 and E1, I1, and here the angle of rotation theta 2 is the moment L2 and E2 and I2. Okay, and now the angle of rotation at the over here, how much rotate here, this will rotate that. So actually what will happen is like this way. It will rotate this much, then this will be simply theta. Okay, so I can draw like this way, and this way, this much, and there will be an angle of rotation theta. So theta is simply, this will rotate this much. That is the theta 1, and this one rotate theta 2. So simply the final theta will be geometrically theta 1 plus theta 2. So this one, if we add them, moment will be a same, which we already know from the equilibrium, and L1, E1, I1 plus L2 and E2 and I2. So from this, we can find this moment and theta relations. Okay, this is the two beams in series, and beams in parallel connections. Now parallel, we can consider two beams in concentric positions, but just for different considerations, we consider two beams are connected, and on the right hand side, and then at the junction we apply the bending moment like that. We can and then what will be the angle of rotations here? Okay, angle of rotations at this point. So we have to consider this is the moment M1, and this is the moment there is a sign we need to consider, but this is obvious. This is the M1, and this is the M2. And equilibrium wise, at this point, this M, the moment we applied, should be M1 plus M2. And then actually I should draw this way. This way, and this one, it should be this way. Okay, so these two moments should be same as the moment we apply. That is the force equilibrium. And the first one, the angle of rotation should be phi1, is theta 1, should be moment 1, L1, and E1 and I1. And theta 2 of this second beam is theta 2 is the moment 2 and L2 and E2 and I2. And that is the angle of rotation for each beam. But here, the most important geometric condition is that theta 1 will be same as the theta 2 because they are connected together. So this angle rotate and this angle rotate will be the same, and which is the angle of rotation we want to calculate. So that is the one of the key points. So the if we put it here, moment now moment M1 is here, and theta will be theta 1 will be theta. So theta and E1 I1 L1 plus and another M2 is here. So E2 and I2 and L2 and theta is there. Okay, so this is the equations for beams in parallel. Okay, this is the relations between a moment and theta, and that is the beams in parallel. And now these beams in series, this is the equations. This is the equations. This is the moment we apply, and this is angular rotation theta we get. Well, obviously there is a very similar analogy between bar and torsion and even bending moments. So I don't need to repeat again, but we need to understand all the three structures, bar and torsion and beam, they behave very similarly in terms of stiffness and deformation and force equilibrium wise. Okay. Now, for the case of a beam, we have a very, very important issue, which is the deflections. And in torsion case, okay, I just like to remind you that in the torsion case, we have a the deformations we obtained was that just a phi is the TL over GIP. That is the a rotation at the top ends where the torsion is applied. That's the deformation. That's all deformation we are interested in. But in beam, there is another very important issue is the deflection due to a bending. This is the additional topic we have to add to a previous equation, previous this derivation. Previously, we obtained all the beam theory, and that is the additional subject we have to consider. Actually, what we want to do in beams is that, okay, let's first review the problem statement, okay? And here are the beam. Beam case is much more complicated than any other structures, such as a bar and shaft. And beam, again, is really extremely important structures supporting many different vertical load. For example, this is the beam. Okay, this is a beam. At the left-hand side, we could have different types of a boundary condition, which we will need to study. And vertical, the load-wise, we could have three different types of a load. First one is the distributed load, QX. So QX is a sort of this kind of distributed load. Okay, distributed load means that a Newton per meter in terms of a unit. And another load type will be a concentrated load, P, which is applied to a certain position. Certain position, we apply the concentrated moment. So the unit will be just a Newton. And another important moment, actually, which we already consider applied to a beam is just a pure concentrated moment, bending moment at a certain point. So at a certain point, we apply the concentrated moment, and this moment can be applied not only at the middle of the beam, but can be applied to an end. That was the case we considered in previous chapter. So the unit should be Newton times meter because simply it is a moment. So again, there are three types of a load: distributed load, concentrated load, and concentrated moment. And of course, we are given the cross sections. Cross section means now we know that the I, there's a bending moment, a moment of inertia I, and material properties. Material properties is the Young's modulus E. That is simply give us the bending stiffness. So we can say EI. EI is always the terms which are multiplied to each other and giving us the stiffness of bending beam structures. And that is the geometric and the material properties. And also the load we apply, external load, this QX or P or M, those are load applied along the beam, and in generally speaking, they can be a function of X. Okay, that's a load. And boundary conditions at both ends. We need to have some boundary condition here. You can think of, let's say, it can be clamped, and it can be free, and it can be a simply support, which we will consider later. So we need to have a boundary condition. Say this is X equals 0. We can say that starting X equals 0 and X equals L. So at the end, on the right-hand side, we need to also apply the certain boundary condition. So again, please remember this. To solve this beam problem, we always have to have a EI, cross-sectional bending moment of inertia and material property, and simply EI and boundary conditions and both ends and external load. Load we need to apply. And of course, the beam configuration, we will need to have the length L. See, this one, I hope you remember that 3 plus 5 plus 1 flow chart, and the 3 on the left-hand side, there are all the forces, right? This is the forces. And the second, there was a material property. This is a material property. And third one is the geometric constraint, geometric condition. That is the boundary condition. So always in structural problem, we have to be given those 3 information to solve the problem. Now now we are given this information. Now what do we want to do? What we want to do is that to find first the vertical deflections. Vertical deflection means that this beam will deform like that, certain deform. So this much deform, and so all the well, we can say the V, okay, V. Actually, we can consider deformation of the midline. Okay, that was the midline, and this midline will have certain deformation, something like that. Okay, so this one we can say that is the Vx. This is the clear. Okay, this is a Vx, and this is the deformation, vertical deflection, Vx. So y-directional deflection, this is a y-directional vertical deflection as a function of x. That's the one we need to solve. And then bending moment distribution, mx. What does it mean is that along this cross-section, every cross-section, there will exist a certain moment, and here moment, here moment, and here and moment. So moment is the function of x, and this is the bending moment. Once we have a bending moment m at x, we can calculate the moment, the tensile stress sigma. If this beam consists of only one material, we can say that force divided by I times y. There is a minus. That is the bending stress at x and along the y. And another one is a shear force. Shear force is not so important at this point, but we can also calculate the shear force. Shear force, and then the shear stress. Well, in calculation of this all deflection, and I need to emphasize the shear force. What we meant by the shear force, shear stress out of this shear force is very small compared to this sigma xx, but the resultant force of Vx can play very important role in equilibrium equations. So anyhow, we would like to have an overview of this beam problem and what are given. This is a given, and these are the deflection and moment or stresses we want to solve. Okay. And I'd like to give you some a idea again, what kind of problem we can have. This is a statically indeterminate problem. Okay, statically indeterminate problem, and statically sometimes a determinate problem. So, for example, say this is the beam. This is a beam. On the left-hand side is a clamped. And then right-hand side, we have a force P here. And over here, on the right-hand side is a free. Okay, then we always need to calculate the reaction force at the end. So here we need to have some reaction force. What kind of reaction force we can have? Well, reaction force could be a moment and another force. So from equilibrium, okay, from equilibrium we can easily get V equals, let's say this is the, I will say R, okay? This is the M0. And this is the reaction force which were unknown, but simply if we use the force equilibrium, then simply the moment equilibrium equal M0 if with respect to this point, total moment applied to this beam will be M0, and this is the simply okay, this is the plus M0, and so this will be a minus, and this P times L will cause another minus P times L. So this will be simply 0. So we can see that M0 is minus P times L. That is a reaction force. And another equilibrium is that vertical force Fy, total Fy equals 0. So the R is a plus. We indicate here plus, and this one indicate the minus. So this is a 0. So R equal P. And well, this one is the afterward. Okay, afterward. So from this and that, we can say they can be calculated by equilibrium equation. So there were two unknowns and two equilibrium equation, and we got these two reaction force. This is a statically determinate. I'm sure we covered this subject in the force equilibrium the very beginning of this course. So this is the simply statically indeterminate problem. And the reason, again, I want to emphasize that this statically determinate, indeterminate is that to calculate or calculate all the deflections, we have to be able to solve this statically, not only indeterminate, but determinate, but also indeterminate. So indeterminate case is we have the clamped here. So we have a reaction moment M0 here, and there is a reaction vertical force is R1 here. And then on the right hand side, we have another boundary condition. Is a simple support. A simple support means that it supports only vertical load, not the bending moment. So it allows the rotation Okay, it allows a rotation, but no vertical displacement is allowed. So there will be a R2. We will study more about this simple support or this clamp. Okay, this beam is subject to a vertical force P at the arbitrary position. Now, how many unknown do we have? We have unknown M0 and R1 and R2. And there are 3 unknowns. And obviously, same as previous, we have only 2 equilibrium and moment equals 0 and force vertical, okay, vertical y equals 0. Actually, this is the moment, z directional moment equals 0. So we have 2 equation, but 3 unknown, so we cannot solve this reaction force just using force equilibrium. So obviously, this is a statically indeterminate case, okay? So again, as I mentioned, the reason I want to emphasize is that this kind of statically indeterminate for this case, we cannot solve these all the three unknowns. So, but now we want to solve that using all deformation condition, deformation, deflection, and so on. So to solve this statically indeterminate problem, of course, including determinate as well, we need to have another equations and to solve this deflections curve. Okay. So in this chapter, we can solve all the unknowns of the beam, which are statically indeterminate, and we can also calculate the deflections, and we can calculate the moment distributions, and we can calculate the shear force distribution at each cross sections. That is the very important. And once we have this one, we can calculate all the stresses, all the stress at every cross section, any cross sections, and we can see that whether this beam is a fail or not. You know, once we have a stress and we compare with a strength or using the failure criterion, we can determine whether a beam fails or not. Okay, that is what we want to do in these chapters. Okay, that is the sections that we want to cover today. Now I'd like to assign you homework, which is due May 9. And the first one is say we have a shaft. Okay, we want to get back to a shaft, and we have a shaft 1, 2, and 3, and subject to a torque at the end, and we want to calculate how much it rotates. The shear modulus is G1 and IP1, and this is the L1, and G2 and IP2 and L2, and G3, IP3, and this is L3. So we'd like to obtain the phi in terms of t, that is the one we want to calculate. Now, the second problem is that we want to exactly same configurations, but we want to have like that and like that. And now we at the right hand side we have a clamp, and here at the junction between first shaft and second shaft we apply the torque T, and then we want to find the angle of rotation, angle of twist. Okay, not this way. And torque we apply, right? This is the torque we apply, and then we want to calculate the phi. Okay, the material property and length is the same as the case 1. Now, the third problem is that a beam, okay, exactly the same configuration, and now this is a beam, and we apply the bending moment, and we want to calculate angle of rotation at where we apply the moment at the end. So this one is the E1 and I1, and this is a length L1. This is the E2, I2, and L2, and E3, I3, and L3. And the fourth question is the same configurations. Okay, same configurations, but at the ends we have a clamp, and then we apply a bending moment between the first and second beam, and here we apply the moment, and we want to calculate the angle of rotation theta. Okay, that is the number 4, and number 5 is that considering beam problem, is very important to understand whether the beam is the statically determinate or indeterminate. Okay, so we have a beam. We have a beam like that. And then we have a clamp on the right hand side, and this is the length L, and this is the length at quarter positions, L/4, and there we apply a vertical force P. Now, is it statically determinate or statically indeterminate? Can we solve the moment, bending moment, function of x? If you can, please do so. If you cannot, please explain why not. And number 6, we have a clamp and another beam, and at the center we have a simple support. Okay, again, simple support, the moment is allowed, and only vertical deflection is the restricted. So always you need to say there is a reaction force, only the vertical forces. That is the only reaction force. But anyhow, at the end, we apply the force P, and same questions. Okay, this is the half, and this is the half, and again, is it statically determinate or indeterminate? Can we solve moment x? I want to also solve a moment x and Vx vertical deflections. And this one is the same thing, vertical deflections. I'm sure you can easily answer whether it's a statically determinate or indeterminate, but not sure you can solve for moment or deflections. If you want to, you can study further next sections, and you can go ahead and try to solve moment x and Vx. Okay, you are welcome to solve moment x and Vx by studying next section. But if you don't, you don't have to. By now, you cannot solve the moment x and Vx. Please explain why you cannot solve moment x and Vx at this point. Okay, that is the point of the number 5 and number 6. Okay, this will be a very important questions for next subject we're gonna study next week. Okay, so this is the end of today's class, and this is the homework is due 9th of May, and hope to see you next week. Thank you. Bye.